So valence bond theory is going to show us kind of how they actually form these bonds to share. And what the theory says, or based on our best, representation of what we can see based on all the evidence around, is that those electrons that are being bonded are concentrated in regions between the atoms. That's why we always draw the lines between them, right? So the electrons that are in bonds are in between. Here's your nucleus, they're in between, right? I'm sure you've envisioned that, right? That's kind of where they have to be to make the atoms stick together. But what's happening is half filled, it's on the wrong size from this morning. All right, half filled atomic orbitals overlap. And that's actually how bonds form. So when we draw, we'll do a real simple Lewis structure. When we draw F2, okay, looks like this. That's our Lewis structure. This part right here, the bond, what's happening is inside of an F atom, so think about F, it's got 2 and it's 2s, and then it's got 5 and it's 2p, right? That would be each of their little electron configurations. And what they're doing is they're taking this one little electron inside of a p orbital, and that's the one that it's sharing with the other fluorine atom. What do p orbitals look like? Dumbbells, right? They're like the little dumbbell looking shape. So what's happening is this little fluorine, and you have to bear with me on my ability to draw. There's its half-filled p orbital. There's one electron in there. It lines up with the other half-filled p orbital from the neighboring fluorine, and this overlap is where the bond forms. So you are taking half-filled orbitals and you're overlapping them, right? In something like HF, right, the F has that half-filled p orbital. Okay. What's H's electron configuration? 1s1. So what does an s orbital look like? Well, sphere in 3D, but yes. All right, so its little sphere is overlapping. All right, so every time we're drawing our little lines between our atoms, what's happening is that half-filled orbitals, so think back to s's and p's from last unit, are overlapping. Does that make sense? You're like, okay, that's good so far. This isn't bad. Here's the problem. What angle are between all of the p orbitals? Remember how there's 3 sets? It's not 120. When we draw them, we'll go back. Here's my electron configurations. When we draw them, we always draw them up, down, left, right? So what angle is between them on an XYZ coordinate plane? 90. So if all we're doing is overlapping orbitals, every bond should be at what angle? 90. And we know that that's not true, right? We know that there's one at 9.5. We know that there's 120. Right? Those angles have been measured, right? They know what the angles are, right? So as nice as it is to think, okay, they're simply overlapping, to make some of the other angles, there has to be something else going on, right? And that's the hybridization part, okay? So we're gonna look at probably a couple, 1 or 2, and then we'll just shortcut it. I won't go through the whole process with every shape. All right, so let's look at BF3, all right? All right, so this is the one I'm trying to make you think about. So how do we account for the fact that there are 3 bonds in BF3, boron's an exception, so it would have this Lewis structure, right? And they're not 90 degrees apart like p orbitals would be. They are 120 degrees. Okay? So there was a man, Linus Pauling, who is the guy that kind of modified our little approach, our idea that the half-filled orbitals overlap, and this idea called hybridization. And what hybridization is we take the orbitals we have, our s's and our p's, and we mix them to make new orbitals. Okay? And that's what the hybridization is. We call them hybrid orbitals because they're not going to look like an S and they're not going to look like a P. They're going to have their own unique shape. Right? And so this is kind of like the logic of like how this is going to work. And I told you if this part seems crazy, it's fine because we're just going to fill things in on our chart. And as long as you can draw the Lewis structure and tell me what shape it is, you can tell me what the hybridization is. All right? It always goes with the same shape. Like linear always has this one. Trigonal planar always has this. So they're always going to match. Okay? So we're going to go start with linear. And we're going to start with a very strange Lewis structure. For a lot of reasons, BeF2. If you looked on the periodic table, you're like, Be is a metal with fluorine. Metal with a nonmetal should be what kind of bond? Ionic. It's not. All right? So like it breaks a lot of rules. And it's a crazy exception. We know what the angle is between them. We know that it does not behave like an ionic compound. Okay, that's why like our generalization of things, like, falls apart. Humans like to put things in categories, right? Like we like to make it has to be this way. It's not the way it exists always in the world. But this is what the Lewis structure would look like. It's a very strange exception. No AP would not ask you about it, but I didn't want to do the double bonded ones for other reasons. So we're going to stick with the weird one. What geometry are you if you have two domains and they're both bonds? Linear. Okay? So this is a linear geometry. Okay? So this is what they do. All right? If you look at beryllium, and we look at just its valence electrons, because I don't really care about the non-valence electrons, beryllium is 2s2, and fluorine is 2s2, 2p5. Okay? So if we think about this, our whole logic is that we overlap half-filled orbitals. Does beryllium have any half-filled orbitals? No, right? Its S is completely filled. Okay? So what the what the beryllium does is it separates the two valence electrons into different orbitals. So we're going to separate them so that we can have our half-filled orbitals. Okay? So we're going to keep one in our little 2s, and then we're going to pop one into one of our 2p's. Okay? And we just talked about this. An S and a P is not going to give you that like 180 degrees that we need. Like the P does, but the S is kind of funky, right? Because it's a spherical shape. So what we're going to do is we are going to what's called hybridize. And we're going to take our 2s and 2p and make a new orbital. All right, now, however many orbitals you put in is how many you're going to get out. They're going to be hybrids instead of S's and P's. So we're going to take an S and a P, so there's two orbitals. We're going to hybridize them. So we're going to get out two new orbitals. Chemists are not creative. I've been telling you this for how long? All right? We name them an sp orbital. Why do you think we call it an sp orbital? It's an S with a P. All right? So you're going to get two new orbitals that are called sp. And you can put the two in front or not. The level doesn't matter because it's always going to happen this way. And then you've got your little p orbitals that are still just chilling. Those are not part of bonding. Those are still just there. And it puts these two little electrons into those hybrids, and that's how it's going to make it. I'll show you the picture in a second. I think you can probably see it in your notes. So first thing, and this is what you're going to learn if you have your chart handy, this is what you're going to fill in on your chart. To be linear in shape, you have what we call an sp hybridization. So on your linear on the front, put sp. That's the hybridization for anything that's linear. And this is what it looks like. So it takes its S, which is a sphere, and it takes its P, which is a dumbbell, and they were really nice, and they did it colors, so they made it blue and red, and when blue and red mix, what color do you get? Purple, so the hybrids are like a purpley color. So when you take these and you mix them together, think like art class, you're mixing them, they're no longer going to look like one sphere and one dumbbell. Your hybrids always make these funky shapes. Okay, so you get two hybrids. Side note, your hybrids always look like this. They have like one little tiny side and then one really large side. And that's the side that's going to do the bonding. All right? So your little beryllium atom takes this hybrid and points it in this direction. It takes this hybrid, points it in this direction, and then where do the fluorines come? They come and they bond right there on the side. All right? So again, like, what do you have to know? Linear gets what little hybridization? SP. All right? Like, that's what you have to know. Here's how I tell you to learn it or memorize it if you're looking for, like, how am I going to keep track? There are 2 electron domains in linear, agreed? Guess how many letters there are in its hybridization? 2 letters. Okay, you use 2 orbitals. So we're going to follow the pattern. The things that have 3 electron domains, guess how many letters they're going to have? 3. And then the ones that have 4 are going to have 4. Okay? So like I said, at the end of this, if some of it's kind of funky, that's fine, because ultimately, if you can draw the Lewis structure, you can match. I have faith in you. Okay? So let's look at the other ones. So boron trifluoride looks like this. All right. Got your little F. It's a weird exception. All right. And again, if we look at their electron configurations, all right, boron starts off, and I'm going to just do valence electrons because it doesn't matter. It's got 2 in its S, and it only has 1 inside of its P. Okay? So the first thing the boron, it's only the middle one that gets hybridized, by the way, also. It's like it's center atoms that hybridize. So the little boron, first off, to make 3 bonds, it's got to have 3 unpaired electrons. So the first thing it's going to do is separate the ones in the S. So it leaves 1 in the S, and it puts the other up in the P. And then it's going to have this one little P orbital that just chills. And then from there, again, to get the right shape with the right angles, to be able to orient them at 120 degrees, right, because the P's are at 90, so that's a problem, we're going to hybridize. This is separate, if you want to label. And they're never going to ask you to do this. Okay, they're literally going to ask you, what is the hybridization of this atom? That's all they're ever going to ask you. So we're going to hybridize. So this time again, we're going to take 3 orbitals. So we're going to get out 3 hybrids. Okay. And in these ones, you put in an S and 2 P's. So guess what we're going to call them? SP squared. They read it as SP2. Okay. So all of these are going to be SP2 hybrids. And then you've got that one little P orbital just chilling off by itself that we didn't use. Okay. And then those are going to line up to make the 120. So these will line up to be 120 degrees apart. And again, it's strange. I know, it's weird. Right? But if we look at what it does, here it's taking its S and its 2 P's, so again, blue and red, we mix them all together. You always get out these funky looking shapes where it's got one small side, one big side. The big side is what's going to make the bond. And for this, again, we're going to spread out as much as we can, which is why we stick to the corners of a triangle. Okay. So on your giant chart, if you have 3 electron domains, so that would be trigonal planar and the first bent, your hybridization is sp2. 3 domains, 3 letters, SPP, but SP squared. It's a very weird little thing, I know. Same thing's going to happen with CH4. Okay, so there's your 4 bonds. Again, we know that the angle is 109.5. We have measured that angle in multiple compounds, so we know that's what it does. But p orbitals are always at 90 degrees, so there has to be something else going on. So again, your little carbon, and it's the center, again, like the outer one just kind of overlaps whatever it's got, but the center one is the one that's going to do this to get the right angle. So your little carbon starts with 2 in its S, and it's got 2 in its P. Again, we have to separate them first, so we separate them. And so it'll put 1 in each of those orbitals. Again, you don't have to write this all out if you don't want to now. I mean, like the Y is not as important as that last column on your giant chart. And then it's going to take all 4 of them, and we're going to make our hybrids. So you'll get 4 hybrids out. You took an S and you took 3 P's, so guess what we're going to call it? SP3. And again, it's going to have those funky, like half-sized, weird-looking things. I don't know how to describe them. Half a lobe, it looks like half a p orbital, kind of. And so it'll take it and it'll arrange it in the shape of a tetrahedron. Okay? So again, on your giant chart now, if you are tetrahedral, if you are trigonal pyramidal, and if you are the other bent, your hybridization is SP3. Okay? Now you'll notice on the back of the chart, we blacked out the thing. So chemists used to think that the exceptions to the octet rule, right, the ones that are the 5 and the 6, they use their d orbitals to make bonds. So it would be like sp3d or sp3d2. That's what it was when I took AP Chem. Now they're pretty sure that that's not what's happening, that actually in the exceptions, 4 of the bonds are covalent, but some of the other bonds are ionic. So it's like a mix of the two. So like that's why it's all blacked out on the back of your test, because they no longer believe that's what's happening based on like obviously current evidence. So you only have to know it for the front side for it. Kind of, sort of makes sense. Very strange. Here's the one for carbon. So it takes its S, its 3 P's, makes the funky looking purple ones, puts it into the corners of the tetrahedron. Right. Try it. Turn to your friends, whoever's around you. Draw some Lewis structures. And then the center atom, what's the hybridization? Go. You don't need to draw a resonance if it does have resonance, just draw one, because it'll be true for all of the resonance. You can like talk to a person, you know. I know the desks like this make it like awkward. I'm sorry. Hey. Okay.
So I don't know how close, how far.
We'll just make the kids come up. Just put it wherever you can put it, and we'll figure it out. Because I have the whole gym, so I'm not like.
Okay. Middle facing the bleachers. Right.
Yeah.
Okay.
Yeah.
I think I'm in the right place, right?
Are you in the aux gym? Yeah.
Downstairs.
I always do the, yeah, it's just easier to do the aux gym than the real gym. Well, I guess I could do the real gym, but I think we did the real gym last year. But I put aux gym, didn't I?
Yeah, I don't know the difference. That's from going down. That's from going in from downstairs.
Yeah, like by the weight room.
Gotcha. Okay.
And just put a TV in there,
Yeah,
and
yeah,
as long as it's
get it
unlocked,
plugged in.
we're good.
Yeah, they have log into the Apple TV.
Is there a password on it, or will it be able to AirPlay without it?
It's just everybody. It's no password.
Beautiful. As long as one of my students can AirPlay.
But I'll make sure you're good. How long it started? What, 12:15?
12:20. It was whenever Warrior Bell starts. I think it's 12:20. So
1 o'clock.
yeah.
Okay.
Yep.
Gotcha.
Thank you so much. And while you're working still, realize that if you draw a Lewis structure wrong, and then the question asks you for like the angle or the hybridization, and you do it correctly for what you drew, you will get those points, right? So like wrong answer carried forward, like if you do it correctly for your wrong picture, you will get the points for that. Just giving you a heads up. So like missing a Lewis structure does not mean you then also miss everything else for your response-wise, right? AP, oh, I didn't mean to have it up on the screen. Don't look at my answers. Why is it not stopping? Rufus distracted me. I blame her. of your teachers make you sit like this every day? Aren't Wolford's desks like this? Aren't they separated? Minimize the amount of talking you can do. This is, I mean, I don't know. Okay, well. I mean, it was on the screen because Rufus distracted me, so blame Rufus. It's all his fault that I got distracted. But ultimately, it is draw Lewis structure matched to hybridization. So again, the first one when you draw it, it is trigonal planar. It has 3 domains. So anytime you have 3 domains, you're SP2. Okay. Second one, when you actually draw it, it's bent, but it's the bent that has 4 domains. That's the only one you gotta be careful, like which bent is it? If it has the 4 domains, it needs the 4 letters, so it's the SP3 version. This one only has 2 domains, so it gets the 2 letters, it's SP. And then the last one has 4 domains, it'll be SP3. Right? So again, it's a memorization thing. Trying to make it not just flat out memorizing. If you can count your domains, you can count your letters kind of thing. Right? Is that okay? Weird?
Does it matter where you write the hybridization?
No, it'll just, because the question will be like, part A will be like, draw the Lewis structure for blah. And then part B will say, what's the hybridization of the central atom? And just put the answer. Because AP, Chem, I don't know how other APs do it. Part A, question, you have a blank. And then B, you have a blank. Like, that's how your tests are. I do it like that, like that's how your test is gonna be. Even this year, with the multiple choices going to online, the free response, you are still answering in a booklet. So you still will physically write your answers. I fear for the day where they make it go online because I don't know how you're gonna type like conversions. I don't know. So just be glad. Multiple choice, I think you're all fine like picking multiple choice online. I don't know how free response will ever go digital for Chem, but we'll see. All right, last thing is how do you make multiple bonds, right? So like, where the double bonds come into play. So everything we talked about so far have been where your electrons are between the nuclei. All right, so again, your little hybrids, your little funky looking, here's your like funky hybrid, looks like a fish, right? And here's your other funky hybrid, or your orbital, whatever, they overlap, okay? So they're in between the nuclei. That's a nucleus of one. There's your nucleus of the other. All right, so when they overlap their little half-filled orbitals, okay, they're in between the nuclei. Okay? And chemists call this a sigma bond. And that the little whistle is the Greek letter sigma as a lowercase. You all are used to sigma as an uppercase in math class. It's like the summation one. It's like an E, right? But that's the Greek letter as a lowercase. And what a sigma bond is a covalent bond where the electrons in the bond are along the internuclear axis. Fancy way of saying between nuclei. All right, so again, nucleus, nucleus, here's where your electrons are chilling, right between them. Okay? Like you've always drawn, like we draw the line and you're like, oh, okay, like that's where the electrons are. They're hanging out between those 2 atoms. Okay? When you make double bonds or you make triple bonds, they don't overlap in the same way. So instead of overlapping end to end, like we've been drawing, when you make a double bond or a triple bond, they make what's called a pi bond. And the overlap here is actually above and below that axis. So what happens in a double bond or a triple bond, all right, if we look at SiS2, we just drew that one, right? So it has this as the center, all right? So what happens is it makes the hybridization, which we know is the SP. So it uses its S and it uses one of its P to make the hybrids. And then it takes the other P orbitals that it has, and instead of overlapping end to end, they overlap next to each other. So it's kind of funky, yet again. Here's my, and you have to go with my drawings. I'm not great at it. So there's one, and then there's the other. And that's not the best overlapping I could do. I'm doing my best. They overlap above and below the nucleus. Okay? So it's just a different way of forming the bond. They form it, again, it's still overlapping of the orbitals, but instead of overlapping end to end, they actually take those p orbitals that they didn't use to make hybrids, and that's what they overlap. Right? And then this is where resonance comes in, is that you really take all of those empty p orbitals, and that's how like the electrons actually move. Like in SO2, again, we don't have a double bond and a single bond. These electrons can move between both of them. It's kind of a funky little thing. Now, what do you have to be able to do in AP? You gotta be able to count, all right? How many of them are sigma bonds? How many of them are pi bonds inside of your Lewis structure? So again, even if you're like, ooh, this overlap stuff is very strange, you can still get the questions right in AP, all right? They're not gonna ask you how or why they form. They're gonna ask you, is this a sigma bond or is this a pi bond, okay? So this is what you have to know. A single bond in your Lewis structure is a sigma bond, always. So when you draw one line between your little atoms, sigma bond, okay? So if we have X bonded to X, this is a sigma bond, all right? When you have a double bond, okay, so you draw two lines between them, right? One of the bonds is a sigma, and one of them is a pi. So like the initial bond is always sigma, the second bond would be a pi. No, it doesn't matter which one you call which. One of them's a sigma, one of them's a pi. Doesn't matter which one. And then crazy enough, if you have a triple bond between things, guess what you got? One's a sigma, and guess what the other two are? Pi. This is what you have to know. Draw out your picture, and you just have to be able to count. All right? And I think you are able to do that. But I have like 2 minutes, so I'm going to draw the next one for you, I think. All right, so we're going to draw this out. It would look like this. Maybe. Just kidding. All right, so your three little H's are going to come out. C, and then it's got a triple bond to the N. Okay? We're going to skip A and B. We're just going to do C for now. And we'll go back if we got time. So it says count the number of sigma bonds and pi bonds. And this is what I do. I just label them in my picture. Okay, single bond is sigma. Sigma, 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 sigma. Which I know my child says sigma all the time and I really hate it. Like it's driving me nuts. And I looked at him and I was like, it's a bond in chemistry. Quit saying the word. So they told his science teacher that. And I was like, anyway. The triple bond, one of them is a sigma. But what are the other two? Pi. And then you count. 1, 2, 3, 4, 5 sigma. 1, 2, pi. Done. That's what you have to be able to do. It's the last question, I think, on your test. Count some sigmas and some pi's. So even though today's weird stuff, I know, ultimately, as long as you're able to draw it and match it to the right SP, SP2, SP3, and you can count singles and doubles, we're good. Oh my God, that is my password.